In 11.3, we're going to look at vectors and their applications. Basically, when we talk about vectors, we're talking about a array. So going back to 9.1 when we talked about our geometric shapes, a vector is an array, but we can apply it in many real-life situations. One of the most common ways that we apply vectors is to model what we call velocity of an object. So a velocity of an object has its direction that it's going, and also the magnitude of the object, meaning in the practical sense, its speed. So a vector can be used to model the speed and the direction of an object. So here's just a note. When you are writing your vectors, you'll either use bold letters, like your textbook uses, or you can write the letter with an arrow above it to indicate that it's a vector. So going back to rays, remember when we did the notation for rays, we had the arrow above it. So it would go in the direction of starting to ending. So starting would be what we call the tail or initial point. The ending would be the head or the terminal point. So when we talk about the magnitude of a vector, that's just its length. Okay, so again, length is magnitude, and it's what we call a scalar. So when we say scalar, we just mean a real number. So a vector is not a scalar because it has two measurements. It has a length and it has a direction, where the length is its magnitude. A scalar is just a number. So the magnitude or length of the vector is just a number, so that's a scalar. So the reason why we call it a scalar is because when you look at the vector, and if you were to multiply it by a real number, what you're doing is you're changing its scale or its size. So again, the word scalar, that's just a real number. So our initial point, again, that would be the starting point, also called the tail. Terminal point, that's our ending point, also called the head. And vectors are equal if they have the same magnitude and the same direction. So below we have an example of equal vectors. This first pair, these are equal, they're going in the same direction, and they have the same magnitude or length. The next pair looks like they have the same magnitude, but they're not going in the same direction, so these are not equal. And then there's something that we call negative vectors. So basically a negative vector is just the negative of a vector. When you look at it picture-wise, if you have some vector, in this case we have our vector b, notice that this vector is going kind of upward. Its negative is going to be the exact same magnitude or length, but it's going to go in the opposite direction. So in this case, it's going, they're still parallel, but in this case, it's going down. Something that comes up quite a bit with vectors is what we call vector addition. And there's two ways to look at vector addition. Basically, when we add two vectors together, what we're doing is we're taking, so in this example, let's say we're going to add a plus b. So we have the tail of a vector, and if we look along vector a, we end up at the head. Maybe I'll use a different color for this. And then if I'm going to add vector A to vector B, I'm going to add it tail to head. When I do that, I create a new vector. The vector is A plus B, where the tail of A plus B is the tail of A, and the head of A plus B is the head of B. And that's what it looks like geometrically if we were to add vectors together. So we just create a triangle. Another way to look at vector addition is with this, what we call parallelogram property. So let's say I do have some vector A, and I wanted to add it to vector B, and let's just say they share the same starting point or tail. Then if I do add them together geometrically, what I'm going to get is I'm going to get a vector between them. And this vector is going to have the same tail as A and B. But how I figure out its magnitude if I'm just sketching it and I don't have any numbers is using this idea of a parallelogram. If you take vector A and you shift it up, because remember these are equal vectors, and vector B you shift it across so that you create a parallelogram, then the magnitude or length of A plus B will be this diagonal from one vertex to the other. So that's used quite a bit when we're trying to get an idea of what happens when we combine two vectors, what it's going to look like. Now, when we actually subtract vectors, we don't. We're actually adding its negative. So if I was to take A minus B, I would change it to A plus a negative B, because remember, every subtraction can be written as an addition problem. And once I have it written as an addition problem, then I can go ahead and do what I did previously. So if I was going to do A plus negative B, and let's just say that this A and B vector that you see here, so we see our vector A, and our vector B is below. If I look at negative B, remember that's just a vector going in the opposite direction with the same magnitude or length. So now I have these two vectors, A and negative B. If I were to add them together, I would have a vector between them, and I could sketch its length by using that parallelogram property. So that's just a picture way of looking at how vectors behave when we add them. I don't know if you can hear this, but there's a huge cat fight outside my window. The next thing we're going to talk about is what we call a position vector. Oftentimes it's important for us to put our vectors into the X and Y coordinate system. So let's say we have a vector and we place it, as these pictures are, in the X and Y coordinate plane. So let's look at this first vector that starts at negative 3, 2, and it goes to 4, 5. Well, this vector, I can place it anywhere in our coordinate system. So why can't I just shift it down so the tail is at the origin, the point 0, 0? Same magnitude, same direction. So this is an example of two equal vectors. Doesn't matter where I put it in the coordinate system, they're still the same magnitude, still the same direction. So why not put the tail at the origin? It's going to make the math a lot easier. And the reason why it's going to make the math a lot easier is because now I can describe this vector by just using the single point. In this case, it would be 7, 3. I don't have to use 2 points because the starting point is the origin. So if you have a vector in standard position or a position vector, that just means that its tail or its initial point is at the origin. So that means that we can describe it using its terminal point or its head, that point where it stops. Now we're going to look at these coordinates A and B in this graph here. A corresponds to an X value. Oops, I don't want to do that. Sorry. So A corresponds to an X value and B corresponds to a Y value. So if we look at this graph and we look at our position vector, this A would be this distance along the x-axis. What we're doing is we're just going to form a right triangle. And B is going to be this 3. This would be the distance along the y. So this would be the A and this is the B, and we form a right triangle. When you think about the magnitude of this vector in a right triangle, that would be the length of the hypotenuse. And we'll use that pretty soon. But since A is this length along the x-axis, which is a horizontal length, we call it the horizontal component. So A is our horizontal component of our vector. B is a vertical length, so it's called the vertical component. And then this brings us to the formula of how we actually compute the magnitude of a vector and how we compute the direction of a vector. looking at this diagram here, we see we have a vector in standard position or a position vector. So if you have a position vector, you will have the point. In this case, the point is 4, 3, which is its terminal point. That's where it ends. Now we're going to go ahead and drop ourselves a right triangle. Where the horizontal distance would be this 4, and this vertical distance would be the 3. So to compute the magnitude or the length of this vector, we would use the Pythagorean formula for right triangles that a squared plus b squared is equal to c squared. And here the c squared, that would be the magnitude of the vector squared. And since the magnitude is a length, when we compute the magnitude of the vector, so we're going to have our vector, in this case, we're calling it u, we're going to put absolute values around the vector so that we can make sure that it's a positive value. And this is how we compute the magnitude. Again, that's just using the Pythagorean theorem, a squared plus b squared, and that's assuming your vector is written with the coordinates a, b. And then you would take the square root. And that would give you your magnitude, and this is the notation for magnitude, absolute value of the vector equal to the square root of a squared plus b squared. Here I did want to point out that these brackets here around the a and b, that is vector notation. Going back to the diagram, the parentheses, that indicates a point. So just be careful. If you're looking at a point has no direction, no magnitude, so you use the parentheses to indicate it's a point. But when you're talking about a vector, you don't use parentheses. You would use this vector notation. Sometimes I'll refer to it as vector brackets, and that indicates that it's not a point. This is a vector. It has a direction, it has a length. Going back to this diagram, notice that if I wanted to find my angle, in this case I'll call it theta, and it's going to be a angle direction in the usual sense. Imagine again going around our unit circle, starting at the positive x-axis. If I wanted to find that theta, I have a right triangle and I have the sides opposite and adjacent to theta, so I would use tangent. And that gives our formula for theta. Tangent of theta is going to be the opposite over the adjacent. So finally, let's do some computations. In example 1, we want to find the magnitude and direction angle of u, which is 2, -5. We want to round theta to 1 decimal. So the magnitude, this is the notation we use, the absolute values of the vector u. That's going to be equal to the square root of, so the 2 would be like the a, and the -5 is your b. 2 squared plus -5 squared. This becomes the square root of 29. And that's actually the exact value. It doesn't say to round it, so this is where I would stop. And this is my magnitude. Direction, we're going to use tangent of theta is equal to b over a. So that would be -5 over 2. So this is not one of my usual values like 0 or square root of 3. So I am going to use tangent inverse in my calculator. In my calculator, I get approximately, and I'm supposed to round this to 1 decimal place, so I get approximately -68.2. And this is in degrees. Because remember, tangent inverse will give me values from negative pi over 2 to positive pi over 2, or negative 90 degrees to positive 90 degrees. Since tangent of theta is negative, that means it's going to give me back a value in quadrant 4, but as a negative value. When we're talking about a direction angle, we always want to use the positive direction. So something that comes up is choosing the right direction angle. And remember, we're dealing with angles. There's infinitely many choices for the same point. So first of all, we want to figure out where 2, negative 5, where that vector, what quadrant it's in. So if I go a plus 2 and down to a negative 5, that tells me I am in quadrant 4. But the direction angle I'm looking at is the positive. So I'm starting at the positive x-axis and I'm going all the way around. That's my theta. What I have is a negative 68.2 degrees. So if I subtract, or add, I guess because it's negative, the 68.2 degrees to 360, then I'll get the correct direction angle. So actually theta is going to be equal to 360 degrees plus a negative or minus 68.2 degrees. And that would give me a direction of 291.8. Yes, that is in quadrant 4, and it is positive. Okay, so just be aware of that. Another way that we can write the horizontal and vertical components of our vector, so that would be our a and our b value, is by using trig functions. The advantage to this is oftentimes we won't have the a and the b values, but maybe we'll have a direction angle. So this is an alternate way of writing our vector. If we look at this a value, it can be written as the magnitude of u times the cosine of theta, and b can be written as the magnitude of u times the sine of theta. So if u is some vector ab, then we can also write this as the vector magnitude of u cosine theta, comma, magnitude of u sine theta with vector notation. In example 2, we're going to use a calculator to verify that if a is equal to the magnitude of cosine theta and b is equal to the magnitude of sine theta, that our vector from example 1 comes out to be the point, or the vector 2, negative 5. So since we're putting this in a calculator, we might not get exactly 2 for the a value, and we might not get exactly negative 5. So just to write this down and remind you that in our prior example, we're looking at the vector 2, negative 5. So let's just check that a, which is supposed to be our 2, so let's just verify that 2 is equal to the magnitude of u times cosine of theta. And in our previous example 1, we figured out the magnitude of u. Remember that was the square root of 29? And we figured out what theta was. We're using the positive 291.8. And that was degrees. When I put this in a calculator, I'm going to have to round this because my calculator will not give me an exact value. It gives me 1.999876999. So if you look at that, that's pretty darn close to 2. So that checks out. Let's try B. Is negative 5 equal to the magnitude of u, which was the square root of 29, times sine of theta, which was 291.8 degrees? So again, if I put that in a calculator, I get that it's 5.0000 0, 0, 491, 99. So if you look at this, this is approximately 5, and that checks out. Again, it's not going to be exact because our calculator will round values. Okay, so let's move on to example 3. And example 3 says we have this vector v. It has a magnitude of 30.5 and a direction angle of 42.7 degrees. Find the horizontal and vertical components and then round to 1 decimal place, which means we're going to be using that formula that a is equal to the magnitude, in this case it's v, is what I'm calling it, cosine of theta, and b is equal to the magnitude of v, sine of theta. So the magnitude is given to us, that's 30.5. And the direction angle is also given to us, that's 42.7. Oops. Degrees. And then putting this in a calculator, let's see, we're rounding to 1 decimal place. I'm not going to write the whole thing out. I'm just going to round it to 22.4. And then this would be the horizontal component. B is going to be equal to 30.5 times sine of 42.7 degrees. In a calculator, I get about 20.7. And that would be the vertical component. Okay, so does that make sense? Sure. Because of what I'm looking at is here, the 42.7 degrees. If that's my direction angle, that means I'm in quadrant 1, right? So I'm going to have some vector that kind of looks like this. It's close to a 45-degree angle. And that means that both the a and b, or my x and y values, are positive, and I have a positive 22.4 and a positive 20.7. Moreover, this magnitude is the largest side, because remember, we're creating some right triangle. So although this is not to scale, if this were a 22.4 and this were a 20.7, then that means this magnitude would have to be larger than the 22.4. And it is. It's 30.5, which seems like a reasonable answer. So again, just be careful when you're putting a lot of things into a calculator. Sometimes there can be error. So you always want to look at your answer and think, is this a reasonable answer? So the next thing we're going to talk about is we're going to talk about vector operations. And what this is just looking at how we would add our vectors, subtract our vectors, multiply them by some real number or scalar. And it's going to be component-wise. So we looked at what it looks like picture-wise when we added and subtracted vectors. But what does it look like if you have numbers? Well, here, if you are taking two vectors, and we'll call one vector AB and the other one vector CD. If you are adding two vectors, all you're doing is you're adding them component-wise. So A and C are the first components, or the horizontal components. So you would just add A plus C. And then you would add the vertical components B and D to get your new vector. So whenever you add two vectors together, you get another vector. And then if you look at subtraction, it's the same thing. You're going to take the first components, but this time you're subtracting them. So when you are subtracting vectors, just be careful. In subtraction, order does matter, so make sure it's first minus second. And then you take the vertical component of each and you subtract them. Now let's just say that you are going to go ahead and multiply a vector by some scalar or real number. In this case, k is just representing some real number. What that does is when you multiply a vector by a number, it's either going to make it longer, so it's going to change both the x and y values or the a and b values, or if the number you're multiplying it by is like 0.2 or a number less than 1, it's going to make it smaller. So this is going to change the scale of your vector, but it's going to change the scale for both components. So when you multiply on the outside by some scalar, you multiply it or distribute it to both components. And then if we look at any vector AB, it's negative. It would be the same as if I were to multiply by a -1. You would distribute the negative to both components. We're going to use these properties, and we're going to find the following. A, B, and C. A is 2u plus v. So u is a vector -2, 3, and v is a vector 4, 2. And we're also going to graph these. So I'm going to write out what this is. 2 times u plus v. Because make sure that you're following your order of operations. U is -2, 3, plus v is 4, 2. So order of operations say that we do multiplication first. So I'm going to distribute that 2 in the first vector to get a vector -4, 6. I don't do the addition, that's last as far as order of operations go. And then I'm going to do this component wise. -4 plus +4 will give me a 0, right? Because I'm doing -4 plus 4. And then 6 plus 2 gives me a +8. So when I take 2 times u plus v, I get the vector 0, 8. And if I were to, and this is just a sketch, you don't have to be all fancy. If I were to sketch this vector, the x value or the a value is 0, but the b value or the y value is 8. So it'd be a vector that looks like this. And typically when we label our vector, we would just label it by the point that it ends up in, its terminal point. In this case, it's the point 0.08. Again, just a sketch. I'm not labeling anything on the axes or anything like that. It's sufficient for me just to write the point. Let's look at B. We're trying to find -2 times u, which would be -2 times u, which is -2, 3. Distributing, I have 4, -6. And graphing, I'm going +4, down -6 to get some vector in the fourth quadrant. So again, when I label this vector, I'm just going to label it with the point parentheses 4, -6. And then the last is v minus u, so just be aware that it's actually the vector 4, 2 minus the vector u, which is -2, 3. So 4 minus a -2, which would be a +6. So don't forget you've got a minus negative there. And then 2 minus 3 would give you the -1. So just be careful with those basic computations with negative numbers. I have the vector +6, -1, so it'd be about here. Again, this one's in quadrant 4, as the last one was. The point 6, -1 is the terminal or the head of this vector. Right, so let's look at some special vectors. And these are called unit vectors. They're called unit vectors because their magnitude is 1. And there are infinitely many unit vectors. So think of any unit vector in standard position or a position vector with a length of 1, that would be a unit vector. But we're going to look at two special ones. We're going to look at our vector I. So if you see this I, it's not the imaginary I, it's the vector I, it's bolded. That would be the vector 1, 0. and the vector j, which is the unit vector 0, 1. If you look at this little graph, this is what these vectors look like. I is a vector along the x-axis, and it goes out a distance of 1. J is a vector along the y-axis, and that goes up a distance of 1. So these two vectors are very important because we can write all vectors in terms of these vectors I and j. So any vector u can be written as ai plus v times j. And the reason why you will see vectors written in this alternate form is oftentimes when we're doing computations with vectors, it's nice to keep them in terms of I and j, because when you add or subtract or multiply or do whatever, you're looking at like terms. So imagine if instead of I had an x and instead of j I had a y, we would just be combining like terms. So for some people it's easier to see that way. You'll often see this IJ form in physics classes. So let's just practice. If we were to write this vector 6, negative 5 in the form AI plus BJ, A is the 6 and B is a negative 5. So our vector is going to be 6I plus negative 5J. But I don't need to do a plus and negative. I can simply write this as 6I minus 5J. So again, this is just an alternate way to write our vectors. And we'll just do a couple of these. If B is the vector 0, 9, I can write this. So the 0 would be the A. So this would be 0I plus 9 would be our B. So it's 9J. And since 0 times anything is simply 0, I would write this as 9J. I don't need that 0 there. So something we haven't talked about is what happens when we multiply two vectors. So we really don't multiply them in the sense that you're thinking of. What we instead do is we compute what we call a dot product. So it looks like the multiplication dot. If I were to take the dot product of two vectors, u dot v, then it is similar to multiplication. So let's just say u is the vector ab and v is the vector cd. So what you do is you multiply them component-wise. So we are going to multiply the a times c, and that would be the first piece. But then we're going to add multiplication of the last components, the bd. So this is our dot product, what you might want to call vector multiplication, but it's not strictly multiplication. And we actually use a dot product later on when we want to find the angle between two vectors, which does come up a lot. So let's look at some properties when you have a dot product. Notice that in the formula it's multiplication and addition, and multiplication and addition in mathematics is super nice. We could change the order, it doesn't mess it up. So when you look at these properties, if you have a vector u dot v, doesn't matter the order, you can do v dot u and you'll get the same value. Something that I did want to point out is that when we dot two vectors, we do not get another vector. We get a scalar. So not a vector. When you dot two vectors, you get a number. Let's go back to the properties. Let's see, on B, if you take some vector u and you dot it with the addition of two vectors, you can actually distribute that dot product. And instead of u dotted, v plus w would have to come first if you're following the order of operations. You can get rid of the parentheses by distributing that dot product and have u dot v plus u dot w. And it works the other way as well. If you are adding two vectors and then you're doing a dot product, you can distribute that dot product on the outside to get u dot w plus v dot w. If you are multiplying a vector by some scalar real number k, and then you're doing a dot product, you can actually pull that k out, do the dot product first, and then multiply by k. Or plus, you could do dot, well, you know what? This should be an equal sign. Typo. That should be an equal sign. Okay. Okay, glad I got that fixed. So there's three equalities here. Basically, it doesn't matter the order that you multiply by that scalar k. You could do it first, you could do dot product first, or you could do it to the last vector, then do the dot product. And then if we look at property E, if you take the 0 vector dotted with any other vector, it's going to be the number 0. And here, when we look at the 0 vector, that is this vector 0, 0 with vector notation. It is a vector. So if you dot that with any vector, you're distributing and multiplying by that 0 to both components. So you just end up with the number 0. All right. So let's compute the dot product in this next example 6. We have our vector u, negative 2, 3, and the vector v, 4, 2. If I were to compute the dot product, u dotted with v, again, that's negative 2, 3 dotted with 4, 2. You multiply the first component, so that would be negative 2 times 4 plus multiply the last 3 times 2, which would give us a negative 8 plus 6. And we get the number negative 2, not a vector. So again, what's the purpose of this dot product? And that's going to be in this next formula that we see. This next formula is going to be the geometric interpretation of a dot product, and what it's for is to find the angle between two vectors. So let's just say that theta is the angle between two non-zero vectors, and here it's u and v. And here we're looking at the angle between them as just being from 0 to 180. The reason why is, let me just do a quick sketch off to the side. If you take some vector and it's random, I'm just going to pick these two. Doesn't matter where you draw them. When we look at the angle between them, we're always referring to the smallest angle. So notice that that angle will always be between 0 and 180. It could equal 0, it could equal 180, but it's always between 0 and 180. Although there is that other angle, the larger one, that's not the one we're actually computing here. It's always the smaller of the two. And then you would have this formula that we see here, that if you take the dot product of two vectors, it's going to be equal to magnitude times cosine of theta. So in this formula, if we're trying to find the angle between two vectors, it's more helpful for us to actually solve for cosine. So imagine dividing both sides by the magnitude of u times the magnitude of v. That would bring you to this last formula, and this is the one we typically will use. Cosine of theta, the angle between the two vectors, is equal to their dot product over the product of their magnitudes. So if we wanted to, in example 7, find the angle between these two vectors u and v, well, first of all, I need to compute the dot product, and then I need to find the magnitude of each. Now I actually computed the dot product in example 6, but just as a reminder that you, okay, now I'm getting irritating myself. U dotted with V, remember that was -2 from example 6. We already figured that out. So we have the dot product. We need the magnitude. The magnitude of U is the square root of, and I think we actually figured this out as well as in a previous example. That would be the square root of -2, or maybe not, squared plus 3 squared. And then I'm going to keep that exact and write that as 4 plus 9, or the square root of 13. The magnitude of V is the square root of 4 squared plus 2 squared, 16 plus 4, square root of 20. And I'm not going to write that in a simpler form because know that that's 4 times 5. So I can write square root of 20 as 2 times the square root of 5. It's not necessary because this is not my final answer. What I'm going to do now, though, is figure out the angle and take cosine of theta equal to dot product was -2. And then it would be the square root of 13 times the square root of 20. And I could just use cosine inverse in the calculator and figure out what this is. I think I'm going to multiply the 13 times the 20 just because it's easier for me to enter in the calculator if I'm doing the square root of 260. So my theta is going to be equal to cosine inverse of -2 over the square root of 260. And now we have to be careful because remember, once we're using the inverse key function in our calculator, we'll only get one value when there's actually more than one value that we could choose. I get 97, okay, it says round to the nearest degree. So this is 97.125, so it's about 97 degrees. So let me go ahead and sketch this. Actually, you know, for this one, since we're using cosine, we don't have to worry because this formula goes from 0 to 180 degrees. So whatever we put in our calculator, since our calculator for cosine inverse will only give us back a value from quadrant 1 or quadrant 2, then we should be okay. But what I'm going to do is I'm going to go ahead and graph U and V just to double check to see if my answer makes sense. So the question is the angle between them about 97 degrees? Well, let's see, U is -2, so that would be in quadrant 2, -2, +3, 1, 2, 3. So it's some vector kind of like this. And then V is 1, 2, 3, 4, 1, 2. So when I look at the angle between these two vectors, 97 degrees seems appropriate. Again, I'm just double checking to make sure my answer makes sense. Example 8 is an example of using vectors and vector addition, but I am going to skip this and I won't be assigning any problems of this form for the class. Example 9, this is actually an okay example, but I'm going to skip it because example 10 is similar to an example 9, and it's actually a very good example for us to be able to apply this idea of vectors and vector addition. So again, 9, 10 similar, but 10 has more stuff going on. It's not just asking us how far a ship is from the port, it also is asking for the bearing of the ship from the port. So in example 10, we have a ship that leaves port on a bearing of 25 degrees. So this bearing is due north. Now remember, when we talk about bearing due north, we're starting at the positive y-axis, the north mark, and we're actually going clockwise. We're not going in our usual theta direction. So we do have to keep that in mind. It's going to travel 7.9 miles, and the ship is going to turn and go east. And it's going to travel for 4.1 miles. We want to know how far the ship is from the port and what the ship's bearing from. What is the ship's bearing from the port? So this language is a little bit weird on the bearing. When it says what is the ship bearing from port, you just care about the from port part. You really don't care about this thing with the ship. So you just want to know bearing from port. And after we draw the diagram, you'll kind of see what I mean when we solve this problem. So first thing, draw a diagram. Let's see, I'm going to go 25 degrees and then I'm going to go east. So it seems reasonable that I would start about here. And remember, this is my north. About 25 degrees. I'm actually going to draw a really big diagram. I want the space. That's a sad line. And then I'm going to stop. So remember, we went 7.9 miles. And then we're going to go east for 4.1. So not quite half. A little more than half, sorry. So I can kind of draw a representative diagram. So I could see that when I'm talking about the distance from the port, it would be the third side of a triangle. Now, in this particular example, you could easily use law of sines or law of cosines to solve as we did prior. But I am going to instead use this idea of vectors to solve. Because if I look at this first direction, 7.9 miles, it's a direction, and it's going 25 degrees north, 25 degrees, which means if this is a right triangle, this remaining would be 65. So if I was going to describe this as a vector, put my little arrow, maybe I'll call this U. If I look at this as vector U, I have my starting point. Instead of using north, maybe I will call it the X and the Y axis. Okay, so think of that as the X and the Y. I have a vector whose direction is 65 degrees and whose magnitude or length is 7.9, and I'm going to call that U. Now we look at the 4.1. That's going to be another vector. We have tail, head. I'll call this vector V. And basically, when you look at the distance, that's going to be the third vector with vector addition. Imagine adding vector U to vector V. We would get this third vector, which is vector U plus vector V, which means to find that distance, I'm just finding the length of vector U plus V. So that seems simple enough. My first step is to write out the components of U and the components of V so I can add them together and get my U plus V. And then to find this, excuse me, to find this distance, I would just find the magnitude of U plus V. Sorry about that. So our distance, let me just remind myself that the distance that we're looking for is the magnitude of U plus V. And here U is going to be equal to, I'm going to use the A is equal to magnitude of U cosine theta, B is equal to magnitude of U sine theta, because I have my angle, right? My angle is the 65 degrees, and I have my vector magnitude, which is 7.9. Right away, I can write this as 7.9 cosine of 65 degrees. That would be my A. And then my B is going to be 7.9 sine of 65 degrees. I'm going to put it in a calculator. Now I'm just going to round these components to, let's go 1 decimal place. I get 3.3 comma 7.16, 7.2. I don't want to write it out with all the decimal places, which would actually be better because we would get a more accurate answer. But just for the sake of time and calculator use, I am going to round. So that would be my vector u. Now my vector v, the problem is I don't have it sitting in the x and the y plane. It's not in that standard position. It's not a position vector. But if I were to take this vector, the one with vector v with magnitude 4.1, and move it down, because this is an equal vector, right? To, maybe I'll do this in a different color. So move this down. Then it would have the same direction and the same magnitude as vector v. So this vector that I've just drawn is equal to vector v. Think about the direction that it's going in. The direction angle, because I have its magnitude, 4.1. I just need that theta, that direction angle. Well, imagine if this were the unit circle and this is where your vector was. You're at 0 degrees. Which means our vector v can be written as magnitude 4.1 cosine of 0 degrees, magnitude 4.1 sine of 0 degrees. Putting that in a calculator, I get 4.1. Yeah, I don't even have to put in a calculator. Cosine of 0 is 1. So this is just 4.1. Comma, sine of 0 is 0. So this becomes 0. So notice I have my vector u and my vector v. To find u plus v, I would just add these two together. And adding them component-wise, I have the vector 7.4, comma 7.2. All right, so this distance is simply the magnitude of vector u plus v, which is going to be equal to the square root. Again, I did round. So if I didn't round the components of my vector v or the vector u, then I would probably get a more accurate number, but this is close enough. It'll maybe be off by less than a degree, but it should be okay, or really close to less than a unit for the distance, less than a degree for the direction. In my calculator, if I round this to 1 decimal place, I get 10.3. Okay, so going back there and looking at this 3-sided triangle, the longest side seems to be u plus v, so having 10.3 seems like a reasonable answer because that would be larger than the 7.9 and the 4.1. So far it seems like it's okay. So what about the bearing? And this is where we have to be careful because when we talk about bearing, we're talking about due north. So if we look again at our diagram at the very bottom where we started out, we're talking about due north, and what we're looking at is okay, if we were to leave from port, so imagine this is our port, what direction would we have to go in due north to get to the spot that we ended up at? Okay, so this would be the direction due north. And there are many ways you can find that. If we find this first piece, that first angle, then I could subtract it from 90, and what's left over would be the bearing due north. And that angle is simply the direction angle for the vector u plus v, so that would be one option. And there are other options as well. We already have this first angle here, this small piece, that's 25 degrees. So if I can compute the angle between u and u plus v and add those two together, I can also get the bearing due north. And there's other things you can do as well. And you can also go back to using law of sines and law of cosines. And in fact, you could have used law of sines, law of cosines at the very beginning. But we're in the section of vectors, so I'm going to continue to use vectors. So I think what I'm going to do instead is I'm going to find this angle here, theta, for this vector u plus v, and then subtract it from 90 degrees to get the bearing. And the reason why I'm doing that is I actually have all the pieces. So using that, the cosine of theta, now here's where it gets fun. Think about how that angle is formed. That angle is formed with u plus v and this vector. So I'm looking at the angle between those two vectors. This was our vector v that I had shifted down. So when we're computing the angle between these two vectors, which would also be the direction angle for u plus v, what we're really doing is saying, okay, find cosine of theta of the dot product of u, or v, or u plus v, sorry, dotted with v, over the magnitude of u plus v times the magnitude of v. And we pretty much have everything except that dot product. But that's easy enough to compute. U plus v was 7.4 comma 7.2, and I'm going to dot it with v, which we're writing as 4.1 comma 0. And then that's going to go over the magnitude of u plus v, which we found was 10.3. And then the magnitude of v, the magnitude of v is going to be 4.1 because it's just the length, right? And this dot product, notice that 7.4 times 4.1, that dot product is 30.4. Oh, 30.34, sorry. But when I add it to 7.2 times 0, 7.2 times 0 is just 0, so it'd be 30.4 plus 0. So I'm not going to write that. And then down below I get 42.23. So cosine of theta, which would give me that angle, is 30.34 over 42.23. And at this point, I would just find theta by looking at cosine inverse of 30.34 over 42.23, and in my calculator, I'm getting 44.1 degrees. Okay, so remember, that is this. I don't want that. I want this piece. But if I subtract it from 90 degrees, So again, if I subtract that 44.1, I get 45.9. And that would be the bearing. From port. And that 30.3, that is our distance from port, which we would then write as a complete sentence. And that's it for this section. It's kind of a long section, and for some reason this my headphones were cutting in and out, so hopefully this will be okay. Anyway, that's it.